Hello, everyone. My name is Andrei Popovich, and I have with me here Simon Peyton Jones, who you may know as a creator of the Haskell programming language, a very pivotal figure in the community of Haskell. And how are you doing?
I'm fine, thank you. Yes, here in Cambridge. Sun is shining.
That's awesome. Maybe at a high level, you could tell us a little bit about, what is Haskell? Obviously, it's a programming language, but what makes Haskell different, and how did you become involved with it?
So Haskell's a purely functional programming language. Most programming languages work imperatively. That is, they say they have a sequence of steps, do this and then do that and then do that. That's what Python or Fortran or C# will let you do. So in functional programming languages, you program with values rather than with state mostly. So in a spreadsheet, for example, the cells have values and you can write a formula in a cell that says, well, cell A3 is the sum of cell A2 and cell A1. And we don't specify an order in which to execute these formulae. The data dependencies define the order, and the spreadsheet's expected to work that out. So there's a sense in which you're saying what you want the results to be rather than exactly how to compute it. That's a sort of slight oversimplification, but it does as a characterization. So functional programming is like, what would happen if we took programming with values in this way rather than with mutable locations that change their value over time? What would happen if you took that idea really seriously? So at first it seems terribly limited. How could you possibly do anything useful? Spreadsheets are, might be good for writing business models, but nothing else. But we learnt back in the 1930s when Alan Turing and Alonzo Church were working actually in the same institution alongside each other. Alonzo Church was Alan Turing's advisor, in fact. They developed models of computation, so-called. Turing developed the Turing machine, and Alonzo Church developed the lambda calculus. In a way, you can see the Turing machine, which involved changing the values of symbols on a tape, as imperative programming at its most fundamental, and Alonzo Church's lambda calculus, which involved rewriting of terms and programming of the values, as functional programming at its most fundamental. And it turned out that the two were just as powerful. That is, anything you could do with the Turing machine, you could do with lambda calculus, and anything you do with the lambda calculus, you do with Turing machine. So functional programming was, perhaps surprisingly, universal. It could do anything with it. So the question is it also useful? And that we didn't know. So the way I got involved with Haskell was I was interested in, as a university academic, in studying the question of what would happen if you took the functional programming idea seriously? Could you make it into a practical programming language that would be actually useful for doing real things? So Haskell started when a group of us researchers got together and said, well, we're all doing functional programming research, but it sort of adds friction if we all do it in a slightly different language. Why don't we, do something very modest? We'll just agree on a common source syntax so that we can run each other's programs. Right. So, hey, how hard can it be? It'll only take us a couple of months to sort this out, and we'll be done. So we formed the Haskell committee and started designing Haskell as a language with these very modest objectives initially. Just avoid unnecessary and friction-causing diversity in our research community.
Clearly, it's been more than a couple months since that happened. The first standard, was that in 1990?
Around about then, yes. Even then, it turned out to be more ambitious than we expected. At that time, our unifying theme was not just functional programming, but lazy functional programming. So in strict functional programming, when you call a function, you evaluate its arguments and then pass them to the function. In lazy functional programming, you don't evaluate the arguments to a function, you just pass a sort of recipe or func to the function. If the function ever needs the argument, well, it'll evaluate it, but maybe it will never need it. That's why it's called lazy. It's like procrastinating. Postpone all work until it absolutely must be done. So if you've got any work and you don't have to do it now, just make a thunk or suspension, put it in memory, and wake it up later if it's needed. So that was the idea of lazy functional programming. The group of us that designed Haskell were all interested in lazy functional programming. At the same time, there was a language called ML that had become, was gaining a lot of traction, that was a strict functional programming language. So we was, as it were, exploring the other part of this design space. We were interested in exploring the lazy part. So why did Haskell turned out to be more ambitious than we expected? I think it was largely because of type classes. So well into the design cycle, we were struggling a bit with the question of, can you take equality on any two values? Like if you say f of x and y is, if x equals y, then blah, blah, blah. Well, in many languages, you could just, any value admits equality. But, what if they're functions? How can we determine if two functions are equal? It's not all that easy in functional programming to determine if two values are equal. So it's tempting to say, well, this function that says if x equals y, blah, 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 doesn't work over any types of x and y. It just works over equality types, a subset of types that admit equality. So ML had a very special case for equality type variables, which we didn't really like. And then Phil Wadler showed up one day with practically a paper. It was a long email. I still have it, actually. And he explained how type classes could fit into the type system and also how they could be implemented. And that was a big moment because it was a systematic solution to a tricky and pervasive problem we'd been grappling with. The same applies to the numbers. If you say f of x and y is x plus y, well, you'd like that to be true of any numbers that admit addition, right? Not just floating point numbers, not just integers, but also perhaps complex numbers, who knows? So the idea of type variables that range over types that satisfy, that enjoy certain operations, that was clearly pervasive, and type classes nailed that problem. After that, type classes were big in Haskell, and that forced us to invent a more ambitious language, in effect.
And then type classes, they ended up not being, they're a Haskell original, but they're not Haskell only anymore. They're not Haskell exclusive. There are other mainstream languages now, like Rust, that have seen type classes and thought, what a good idea, we'll implement something very similar. Right?
Oh, zillions of languages, yeah. So type classes have proved to be an extremely pervasively popular idea. It was one of those things where it was birthed in a single email by Phil Wadler and Steve Blott, and then and we thought, oh, here's an elegant solution to a relatively narrow problem. And then it turned into a whole research area all of its own. We got multi-parameter type classes, we got type classes with high-kinded type variables, we got functional dependencies, we've got associated types. That lots and lots of stuff were birthed out of this little seed. And as you say, the idea was sufficiently persuasive that lots of other languages have in effect adopted some form of type classes. So in some ways it was serendipitous. It was nothing to do with lazy functional programming at all. You could equally well have done this in ML. It just happened that Haskell was the laboratory or seedbed in which type classes got their foothold.
That's very interesting. Are there some functions in the Haskell standard library that predate type classes? I thought this was the explanation for why there's a difference between map and fmap.
No, nothing really predates type classes. I think the type classes were in the very first Haskell report. I'm almost certain. God, this is going back 35 years. But they were certainly very, very early. Now, at that stage, we had type classes for equality and for numbers, mainly. There was quite a number hierarchy, not just numbers, but real numbers and floating point numbers. There's a whole little zoo of numeric type classes. And those were all in first edition. A bit later on, we realized that we could abstract even more powerfully using type classes. So for functors, if you have a list of t's, then you might have a map that applies a given function. So map takes a function from a to b and a list of a's and returns a list of b's. But perhaps if you've got a tree, you can take a function from a to b and a tree of a's and return a tree of b's. So there are lots of data types, lists, trees, and then you could write more and more and more, all of which have a map operation. So then it's natural to say, just as we say, oh, we've got equality types and numeric types and these little zoo of type classes, maybe we could have mappable types. But unfortunately, it's not a mappable type, it's a mappable type constructor, right? So it's not that list of t is mappable, it's list is the mappable thing, or tree, right? So now the type class has to abstract not over a type, but over a type constructor.
So a type constructor is like, we have some type, like let's say integer, or abstractly we can just say t, and then a type constructor just takes that and changes it. So a list of t or a tree of t.
Yeah, exactly. So list of t, tree of t, those are both types, and values can inhabit those types. But list and tree are type constructors. That is, if you think of the world of types, you might think list of t, like list is a function that takes an argument that is a type and returns a type. So list has kind, type arrow type. It's just functional programming at the type level. That's what functional programmers do, of course. As soon as you see a function, you should see it everywhere, right? So that's why we say that list is a type constructor, and indeed we can give the type constructor a type or a kind, right? Kind and type mean roughly the same thing, right? So we're going to say list has kind, type arrow type. or in Haskell as it was then, star arrow star that we used to write it.
This is the, what often discussed concept of a higher kinded type. When people want to talk about what makes Haskell unique, normally they'll say laziness or purity, but sometimes, if they're getting into the weeds, they'll say, and Haskell has higher kinded types.
This is a big deal. We didn't realize how big a deal at the time, because now you've got to say, well, if I want to say that list is mappable, so for equality, I would, the Haskell type class, right there in the first version of Haskell, said class EQA, where, and then it listed the methods of the class. So class EQA where equals has type A to A to bool, right? And not equals has type A to A to bool. And for numeric, it would class num where plus has type A to A to A, and negate has type A to A. Easy enough, right? Now, what back for mappable things, we'd want to say class functor F, where, and now the method is fmap has the type A to B to f of A to f of B, right? And now we're going to instantiate that little f with either list or tree. So then fmap will have type A to B to list of A to list of B, or A to B to tree of A to tree of B. But we summarize all of those in one method, fmap, with type A to B to f of A to f of B. And that little f, it's a type variable, right? But what's its kind? It's type to type.
So right? It has a higher kind.
Yes. In order to take advantage of Haskell's type classes, which are so useful for equality types and numeric types, in order to use that same power for mappable things, we needed higher kinded type variables.
I think higher kinded type variables they're very elegant because they sort of feel like you're sort of just removing a restriction. Instead of being restricted to only being able to use only just types, you can also now use like type constructors.
Yeah.
In the same place.
That's right. Just lift a restriction. But interestingly, at the time, we said, this was Mark Jones who first suggested this. We said, Mark, look, this is never going to work because we need to do type inference. And so the natural thing at the type level would be to have lambdas, right? At the term level, we got lambdas. At the type level, can't you have lambdas? And now, of course, lambda t dot t, for example, would have kind type to type, like one of these list constructors, right? But as soon as you have lambdas and type inference, then, you're lost. Type inference, which is very important to Haskell, does not interact at all well with lambdas. There's no principal types. Nothing works. Mark's amazing insight was to realize that we could still have higher kinded type variables, but we could not have lambda. No lambda at the type level. We're just going to have some, when you declare a data type like list or tree, you get a type constructor, list or tree, with kind type to type. So you have higher kinded constants, but you have no lambdas. So you can only build things of higher kind by using those constants or maybe by partially applying them. Now that is a restriction, right? Sometimes it's a tiresome restriction, but type inference is dead easy. So this such a simple compromise meant that type inference was no problem at all. And yet we could have higher kind of type variables, so we could do all this mappable stuff. And that was amazing, right? That launched a whole new design space of library design. If you look at the zoo of Haskell libraries with applicative and functors and monads and and then traversables and monad zeros and alternatives, they're all higher kinded. And it all links back to, if you look at it through the right kind of lens, the category theorists say, this is what we do, right? So Haskell became a language in which you could more or less directly express some aspects of category theory. And that was never really possible before. So this little innovation, higher kind of type variables, with its very cleverly chosen compromise that Mark Jones suggested and that we've adopted, 35 years later, we still have exactly the same compromise, that unlocked this great new design space. So type classes have been widely adopted. Higher kind of type variables, not so much. There's good reasons for that. My belief is that the reason is that higher kind of type variables don't interact very well with subtyping. And many mainstream languages have adopted subtyping, particularly object-oriented language, which means most mainstream languages, right? Yeah. So with subtyping, you say, well, if I've got a car it's a subtype of vehicle, and vehicle is a subtype of, I don't know, machine, right? Now, the combination of subtyping and type inference and parametric polymorphism is a complicated one. Very few languages do all of that, and they all have to make compromises to do that. Scala is an example, incidentally. So what's the problem? Well, imagine you're asked to say, is list of T a subtype of list of T1? Is it a subtype of list of T2? An OO language has to answer that question. Well, and it depends whether list is covariant or contravariant in its type argument.
We should maybe explain this a little bit because I'm not sure that everyone in the audience will know what covariant and contravariant means. What it means is if A is a subtype of B, is list A a subtype of list B?
Mm-hmm.
Most people would say
that
yes.
is the question. And you might think, well, obviously yes, right? But you'd be wrong if lists were defined, remember list is just some random old type constructor. I mean, it's a built-in one, so we know about it. But imagine we didn't know. Imagine it was, is S of A a subtype of S of B? Supposing S was defined like this. Are you ready? Data S of A equals S, that's the data constructor, and its argument is A arrow int.
Oh, so A is on the left-hand side of the arrow.
A is on the left-hand side of the arrow, but buried inside the data type S. You can't see that looking from S from the outside. A is on the left-hand side of an arrow.
In subtyping, while you can pass a type that's more specific than is expected, it's okay to substitute a type with a more specific type.
Yeah.
But then if A is on the left-hand side of the arrow, does this create a situation that's that's covariant or contravariant?
Well, it's contravariant because let's imagine that you are expecting me to give you a function of type car to bool. So I'm calling you, and you're expecting me to give you a function of type car to bool. But then I actually give you a function of type Citroen to bool. After all, Citroen is a subtype of car. Surely that should be fine.
But it won't, because if I try and pass a Honda, then
exactly.
I'll have a problem.
Yeah. So because it's on the left-hand side of the arrow, you're expecting something of type car to bool. I'm giving you a Citroen to bool. Wrong, right? Even though if you look at it, I'm giving you an argument whose the little components of the type are more specific. So what that means is you've got to be careful with function arrows, right? Now, you could say, but look, so S1 arrow T is a subtype of S2 arrow T. If S1 is a subtype of S2, but rather if S2 is a subtype of S1, you've got to flip it around, right? Okay. You have to be careful with arrows. And we're in an arrow-full world. This is higher-order programming. So now what happens? So now what happens if that arrow, though, isn't visible on the surface? It's buried inside S, right? So now you're expecting an S of car, and I give you an S of Citroen. Bad.
That's not good. That's not going to work.
That's not going to work.
It's just unintuitive because if I'm expecting a car and you give me a Citroen, that's fine.
Yes.
But if I'm expecting a function that takes a car and you give me a function that takes a Citroen,
exactly, that's not
then
fine.
We have a problem.
Exactly. Yeah. So what that means is that subtyping, you'd have to be really careful with this variance business. And the variance business can be hidden underneath type constructors somewhere, like our S. So maybe we say, well, that's fine. We'll look at S, at the definition of S, and we'll remember that S, this new data type, is contravariant in A.
Okay.
Now you'd be fine, because now you'd have to, the notion of subtyping would have to know about covariance and contravariance. But already that's a bit difficult, because there might be another data constructor of S, which uses its argument A in a covariant way. So now it's covariant and contravariant, so now you have to remember that it's invariant. And then then it can get worse, because now remember, we're trying to abstract over type constructors. So now what happens if I've got, remember that little f in the functor thing? Is little f of T1 a subtype of little f of T2? Oh, man. Well, it depends on the variance of little f. But little f is a type variable, so we don't know it's variant. So all I'm saying, there's a rabbit hole here that gets pretty deep. And I think this rabbit hole is the reason that the combination of subtyping and higher kind of type variables has never really caught on.
That makes sense. I had never realized that before. This concept of variance, covariance or contravariance or even invariance, it's interesting because it sort of shows up all the time in places where you don't really think it would. If there's anyone in the audience who likes to program in Rust, the Rust type checker needs to be aware of covariance and contravariance because lifetimes implement a subtyping relation.
Yeah.
So this is not just a sort of niche Haskell idea.
Oh, no. I mean, subtyping is terribly useful, terribly compelling, and yet interacts very badly with type inference and parametric polymorphism, particularly parametric polymorphism over higher kind of type variables. It's kind
I
of like
see.
a
So
massive fork in the road, and Haskell chose the fork that said, we will not do subtyping. But in exchange, we'll get, wonderful type inference and higher kind of type variables and a whole zoo of things.
would the problem be alleviated if you sort of required all type constructors to be covariant?
Well, yes, but that would be a huge limitation. It's like, now, then your programmers would start bleating at you and saying, but I want to write this perfectly good data type, and you're saying, I just can't write it. That's terrible.
And it would be a very long explanation for why, and no one would believe you that was a really a good reason.
I have a talk I gave a long time ago called Classes Gym, but Not As We Know Them. First gave it at eCoop and European Conference on Object-Oriented Programming. And the slightly contentious point of view, it's a keynote talk, so I thought I should, say something controversial. So what I was trying to say then is that object-oriented languages, their goal is polymorphism. By polymorphism, I mean a single function that works over values of more than one type, right? So OO says, well, I work over vehicles, you can give me a car. So I'm polymorphic in the sense that I will work on any subtype of vehicle, right? That's polymorphism. Polymorphism in general just means functions that work, a single code block, if you like, that works over arguments of many different types, right? Now, parametric polymorphism is a different approach to polymorphism. We'll have a function like reverse with type for all A, list of A to list of A, and parametric polymorphism is not it's not the same as subtyping. It just says, I do reversing on lists and I don't care about the element type. I'll work equally well on lists of ints and lists of chars. Initially, object-oriented languages only had this subtyping polymorphism and had no parametric polymorphism. Right? But over time, object-oriented languages have realized that parametric polymorphism is super valuable, right? So they've grown what they call generics, which is parametric polymorphism. But only over, not higher kinded type variables for the reasons we discussed, typically. And they even grow a sort of form of bounded polymorphism. So then, meanwhile, on the functional programming side of the fence, we thought, oh, well, this interaction with subtyping is really hard. So we never introduced subtyping. We just went gangbusters on parametric polymorphism. But type classes give you something of the same kind of stuff that OO gives you, right? Because if you want to say, look, I'll accept any argument that is a vehicle, well, in Haskell, you would say for any you would say the function has type vehicle A, double arrow, A to blah, right? That is, I'll accept any type A, which is in the vehicle class. Haskell gives you the same kind of flavor as OO, right? But it does it using only parametric polymorphism, no subtyping.
And then you can even have type classes that sort of act like they have a subtyping relation where, you have one type class that's a superclass of another.
Yeah, so it goes pretty far. Now, I'm not dissing OO languages because they've been vastly more successful in practice than Haskell has. It's just like we've got these two forms of polymorphism, parametric polymorphism and subtyping. And OO languages have grown to include both, which is jolly complicated and makes it really hard to do this abstractly over high kind of type variables. Meanwhile, Haskell has said, let's just stick to no subtyping, one way to do so. In effect, the two ways sort of overlap in OO languages. We've got two hammers to hit one nail. The OO hammer, the subtyping hammer, isn't enough. We have to add the parametric polymorphism hammer. Haskell has said, let's take the parametric polymorphism hammer and see just how far you can go. Right? And the answer is really almost all the way. And I feel as if, in my talk I said, maybe it's time for OO languages to abandon the scaffolding of subtyping, that was indeed so important in getting there. But I don't think that's ever going to happen. But it is an interesting design discussion.
Really what they would have to give up on is inheritance. Although inheritance is
so useful.
Definitely useful. Yeah, it's so useful. When people like OO, I think a lot of what they like is the syntax where they can say value dot method, and this is something you could definitely keep.
So interestingly, Haskell has been growing that notation. The extension is called overloaded record dot, and you can say x.f, and that means the application of there's a hasfield class.
Oh, yes, because prior to that you would have to do fx to sort of extract the f field out of x. That's a awesome change. This is a recent extension?
Fairly recent, yes, just in the last year or two. But the whole business about record dots and how to do records in Haskell is one of the less satisfactory aspects of Haskell. The design of a record system is there's a lot of different possible choices, and none of them seem to be distinctively better in all dimensions. And so it's taken us a long time to iterate towards something stable on the record front. But the point about these overloaded record fields is, so when you say x.f, that does not mean that x has to be a record that contains a field f. No, it just means you have to give an instance for the f method. So it's like an extensible type class in a way. So that's good, because it means that you can define any old new function on the type of x and add it to its has field instances.
So I can add my own. It's not just the literal fields that
Exactly.
you can do .f for.
Yeah. You can, as it were, add new methods, as it were. Now, I'm making it sound very good, and I'm sure it has all sorts of quirks and limitations. It's the point about Haskell is sort of a laboratory in which to explore a design space, and we're trying to move reasonably slowly to explore this design space. But I think it's pretty interesting. It doesn't let you do anything you fundamentally can't do without it, but I think it will look and feel very different, and so I'm interested to see how that develops in practice.
That is exciting, and that actually segues into something I kind of wanted to talk about as well, which is this idea of Haskell being a test bed for ideas.
Yeah.
And of course, we've already discussed how type classes were something that was tested out in Haskell, and they ended up being an enormous success. But GHC has this, GHC being the Haskell compiler, has this concept of language extensions. So before something is in sort of the official, definitive Haskell, it can be added as an extension, and then people can enable it on a file-by-file basis and sort of play around with it. Is that right?
Yeah. Initially, we had, the Haskell report, and I was the editor of one version. There was Haskell 98, there was Haskell 2010, and so forth. These were sort of, big, high investment documents. But it became increasingly hard to sustain, in the sense that nobody really wanted to sign up to all the work of getting out a new iteration. It takes a lot of discussion. And so increasingly we've moved towards a situation in which, yes, the compiler implements a couple of hundred extension flags, each of which is meant to enable a specific language extension with a specific document that explains how it works. And then because that means that the top of your module, or you can list at the top of the module which language extensions you're using. So that means that code is sort of self-describing, in the sense that the code says, I'm written in base Haskell, as it were, together with these 17 extensions. But when the first screenful of your module is just a list of extensions, that can get a bit daunting. So I've also tried to move towards a system of defining language additions. This is the terminology taken from languages like Rust, actually, in which you say, well, this collection of extensions we'll call an addition. And Haskell, or I think there's an edition called GHC 2021, and that means a particular bundle of extensions.
Oh, really?
And a few more things in the warning flag settings and so forth. And it's meant to say, well, then you can abbreviate a whole bunch of things. But they're meant to sort of work smoothly together. They're a sort of coherent bunch.
And this alleviates a little bit of the experience that many people had when learning Haskell, which is they would sort of Google what language extension should I enable, and then they'd find several blog posts that give long lists of why I like these ones and not these ones.
Yeah, exactly. It's meant to sort of codify some reasonable extension sets that the people have liked and seem stable enough, right? So the idea is a language addition is probably going to be stable. There's not an absolute promise that it'll never change, but nothing gets into a language addition without having, survived several years of battle testing.
So what kind of stuff are people putting in extensions? We gave the example of the ability to say, add like dot to access a field of a type, but there's hundreds, like you said.
Yes.
Is there anything notable?
The way to find out is to go to the GHC proposals site, because this is how you get to have a new language. It's not just the whim of the developers, which it used to be. Now there's a GitHub repository. Just search for GHC proposals and a committee that evaluates. And a lot of them are, you could think of them as somewhat incremental. Some of them are not specifically language extensions. Like one of the most recent ones is to do with trying to expose a set of libraries for template Haskell, which we haven't talked about, but it's something that the details of which change relatively frequently, but quite a lot of libraries depend on template Haskell, but they depend on it in fairly simple ways. If we could arrange that they could depend on not the whole interface of template Haskell, but only a subset, a stable subset, because they don't need as it were, the full glory, then when we release a new version of GHC, maybe the stable subset bit that they depend on won't have changed at all, and that would mean that they didn't need to have version bounds updated. So one of the things that has changed is paying a lot more attention to trying not to gratuitously break people's code. And one way to do that is by being more fine-grained. So that's one proposal that's opened at the moment. There's another on, let's see, named defaults. This is to do with defaulting for type classes. There's another one on staging syntax. When you use template Haskell, are you depending on compile time changes or runtime changes? And that again helps your build system. So a lot of these are not, large-scale language developments. They're more like, solidifying the ecosystem to make it more robust to changes.
I mean, there are the really fancy ones that you hear about often, like a linear Haskell, which adds linear types. And then even bigger, I don't think this is in GHC yet, although you can correct me, but dependent Haskell has been worked on for quite a while, which I'm sure will be a very big language change once that is able to...
Not really. So it has much more of the characteristics of what you described as lifting restrictions. Dependent Haskell is not a single increment. It's a series of, 20 small increments. And there's several proposals about this, which develop the language. So let me just give an example so that if you, one little step along the way was when you call reverse, usually in Haskell you say reverse of x's, some list x's. But reverse is a polymorphic function, so it actually takes a type argument. So reverse is type for all A, list of A to list of A. So a full call of reverse would look like reverse applied to int and applied to the list 1, 2, 3. So it takes a type argument and then a term argument. Now that type argument is usually invisible. You don't write it in the source program. But it's there in the GHC's core language, and occasionally it's very convenient to be able to write it. So one little step along the way was to allow you to write explicit type arguments by saying reverse @int and then the list 1, 2, 3. They may say it's sort of strictly redundant, but you can figure it out from the term argument. But sometimes it's very, very helpful to be able to write the type argument explicitly. Amazingly helpful. It's a very, very useful extension. Sometimes, as it turns out, it's quite helpful to be able to insist that you write type arguments. Not for reverse, but for some other functions. We could go into why. But then instead of writing foo and then @int and then some term argument, you might write foo int, no @ and some term argument, and you must put it there, right? If you omit it, then you'll just get a type error. So the type argument becomes compulsory instead of optional.
And then the @ indicates that it's a...
The @ says, I'm filling in for an optional type argument. So the type of reverse is for all A dot AOA. The type of foo might be for all A arrow AOA. And that says, oh, the type argument is compulsory. You must write it. And so, in fact, terms and types become a little bit more similar. They just sit side by side. And again, there's a whole, story about this. But for some styles of programming, it can be really, really helpful to have compulsory type arguments. So then there's a whole infrastructure to, just exactly what should the design look like? How can we tell that something is a type? Well, now it looks, if I see foo applied to int, how do I know if that int is a type or a term? Types and terms get a bit more mixed up together. There's a big design space there.
But I see why you describe this as lifting a restriction, because now it sort of seems like I can pass a type to a function the same way I can pass a value.
Yeah, and in fact, in GHC's internal language core, we have been passing types to functions since 1990. One of our biggest initial insights into how to compile Haskell was that we take this big source language, Haskell, and we compile it to this small intermediate language, which is kind of the lambda calculus. But we wanted it to be a typed lambda calculus. But a typed lambda calculus in a polymorphically typed world, well, we could look back 20 years and find System F, which is apparently a very exotic theoretical artifact, from Girard and Reynolds that I learnt about in, my theoretical computer science lectures. But actually, it is the language that GHC uses as its core language. And in System F, every polymorphic function gets explicit type arguments. So while they might be implicit in the surface language that programmers write, they're explicit in the intermediate language that GHC manipulates, and always have been. A lot of this quotes-dependent Haskell stuff is no more than a way to make explicit in the surface language things that were always there in the core language.
Is this the sort of secret sauce that allows the GHC developers to remain productive, despite having to keep track of 200 different extensions?
Yes, in the following sense, that Haskell source language is indeed big and quite ad hoc in a number of ways. That's why if you read GHC proposals, you see lots of, detailed discussions about how many angels can dance on the head of a pin. It's painstaking. And some of it is a bit ad hoc, right? So just how should type inference work, right? So there's a number of compromises that make type inference work. For example, that if you want a polymorphic function to call itself a recursive function, can a recursive function call itself polymorphically? Well, if and only if you give it a type signature. That's a surface language design choice, but in the intermediate language, it makes no difference. So all of that complication is compiled down to this very small intermediate language. And the intermediate language has, it's represented by an algebraic data type, of course, because that's the way we represent syntax trees in Haskell. And this data type only has, about 10 constructors. From all the hundreds of language constructs, blam, 10. Everything goes down to 10. It's it's a really small intermediate language. Oh, and moreover, it's a statically typed intermediate language, so that as we compile, GHC then consists of a lot of passes that go from this language to itself, optimizing it. Now, if one of those passes makes a mistake, there's a variable out of scope, or there's something that's ill-typed. Of course, that should never happen if the compiler is bug-free. But we can have a little type checker, which isn't necessary if the compiler is perfect, but is helpful when you're not sure that the compiler is perfect, that sort of health checks the compiler itself to say, oh, look, this pass produced a program that was ill-typed. Now, look at the difference that has, right? So if the intermediate language was untyped, then there's a bug in some optimization pass. It runs right through the compiler, generates machine code, run the machine code, crash, right? How do you find your way back, right? Now you've got to find out why did it crash. But the machine code was wrong because, and then you have to work all the way back through the optimization pipeline to find out who introduced that bug.
It started being wrong after this pass, but if there's 20 passes.
Yeah, 20 subsequent passes, yeah, that's right.
Yeah.
So it's been heavily disguised. And then finally you have some machine code that you're running, and when you run it, all you get is, I dereferenced the null pointer, or I followed, it's some really obscure and horrible runtime failure. These are incredibly hard to find, right? Contrast that with, you compile the program and blam, after pass 32, a type error.
Easy. It's right there in pass 32.
It's right there in pass 32. It's transformational. So I'm a huge fan of a statically typed intermediate language for keeping compiler developers sane, but it's also useful as a sanity check. Any language design change in the surface language that can still be compiled to the same intermediate language is, as it were, superficial. You can be confident that the whole backend will be fine.
Because the backend is seeing the same sorts of things that it was seeing before.
That's right. It's the same language. It's the same type system. Nothing has changed as far as the backend is concerned. All that has changed is desugaring, or maybe type inference. Now, on the other hand, if you want to propose a language change like, I don't know, concatenable records, right? Then that would imply some actual change in the intermediate language. Now you're into a whole different thing, right? And we haven't made a language change in the intermediate language for, a decade, even 2 decades. I mean, really, it's very, very stable. So it's an incredibly good sanity check on what surface language features are, as it were, fundamental and which are kind of superficial.
And so, this implies that the type system used by the core language, which I believe is called system F omega now.
Yeah, but F omega itself that wasn't extra to GHC. That was, Girard designed that, right?
Oh.
That was a theoretical computer. We just picked it up and used it.
Yeah. So you just picked this thing up off the shelf and used it, and it's been good pretty much since the 90s.
Yeah.
That's pretty amazing.
That's pretty amazing, right? That's theoretical computer science being the practical reality in the guts of a production compiler for 3.5 decades.
I actually didn't know that it was not developed for GHC. I kind of assumed it was just because it seems so perfectly suited.
No, we did extend it a bit. So when we added type families, which also are taken from the world of dependent types and so forth, but adding type families was a significant extension of the intermediate language. But that was, we did that 2 decades ago, and that stayed stable since. But that part is not part of System F directly. It's an extension.
So if someone was writing a programming language now, and they were thinking about having a typed core language, would you suggest System F omega as a good choice?
Well, our extension is called FC, so it's a good search term, System FC. FC is F omega plus data types. Girard was not worried about data types. It's plus data types, including plus data types and type equalities and type families. So it's a significant extension of F omega, but very much in its spirit. So yes, it's not the only choice, but it's a choice that served us very well.
It's interesting because there are sort of 2 sides to types And obviously types are a very important thing to Haskell. The first one is the most visible one, which is that they find bugs for you. You pass a string to a function that expects an integer,
Yeah.
and it doesn't compile. But then the second thing is the types actually can be used to influence how the code is generated. But this aspect is of the types finding bugs for you. It sounds like it's been very useful because it means that anytime you're automatically changing source code, you can check to see,
Yeah.
did I introduce a bug that's detectable by the type system?
There's a lot of debate about the static type systems, but I think they're slowly winning. But for me, the two things about static type systems that are not so often discussed are these. The first is, when you design a piece of software that you want to live a long time, you often have in your head certain invariants, things that are true about the function. Like that it, sort returns a sorted list, and that your customer update returns a database that has some invariants, that every customer lives in here, and every customer that has a customer record has an address, and every address is lots and lots of invariants, many of which are not very explicit. Now, a type system lets you make some of those invariants explicit. Or we could say it like this: a type is like a theorem about your function. If a function has type int to bool, it's a theorem that says, if you give me an int, I will return a bool, or I'll diverge. So it's not a very powerful theorem, but it is a theorem. Or moreover, the theorems with parametric polymorphism become a bit more powerful if reverse has type list of A to list of A. That tells you that because it's for all A, list of A to list of A, it tells you that reverse doesn't mess with the values.
It can drop them or copy them, but it can't sort of add one to any value.
That's right, and it can't take control decisions based on the values. So what that means is that if you took a list and you mapped over it, like to double all the values, and then you reversed it, that would give the same result as if you first reversed it and then mapped double over it.
And you can see this just based on the type signature.
That's the point. So there's a theorem about reverse that reverse and then map is the same as map and then reverse, provided the map is of type A to A. This is a so-called free theorem, which comes from the type of map. You don't have to look at the body of map. You just know it from its type. And this also goes way back into theoretical computer science. It was John Reynolds who developed this idea. It's called Reynolds' parametricity theorem. And Phil Wadler, again, popularized it with a paper called Theorems for Free. The title of the paper connoted the idea. Phil was very good at inventing paper titles. He said, once you have the type of a polymorphic function, from that type alone, I will cough up a theorem that is true about that function.
That's very interesting.
Quite a powerful thing to do. So now, backing up then, types are like weak theorems, but a great advantage of types is that they are theorems that are checked by the compiler every time you compile. And moreover, the language of types is like a design language. You'll often, if you talk to Haskell programmers or OCaml programmers, and you are one, you often start by writing the functions, the function type signatures. You write the API of your library. In OCaml, you'd write the module signature for the module you're about to write. So the types give you a language in which to express things explicitly and in a machine-checked way that would still be there, but implicitly and never machine-checked if you were programming in an untyped language. So they are, if you like, I think of type systems as a design language, a machine-checked design language for software.
It's kind of beautiful. When I was first learning Haskell, I had this realization that the types are like documentation that is always correct and makes my code run faster. And sometimes I don't even have to write it because Haskell can infer it.
Sometimes it's inferred. Now, the second thing about types that I think is less frequently discussed is longevity. So here I'll again make a contentious statement, which I'm very interested to, if people can, to actually have data about this, because I do not have data. But my impression is that when you have large code bases written in an untyped language, that 2 years after it's been written, the developers themselves are a little anxious about modifying it, lest they break it, no matter how many tests they've written. And when those developers have left the company, then it becomes increasingly difficult to modify that software at all. So then software becomes sort of frozen in time, and then we have to sort of work around it from the outside. We don't dare modify it, so we sort of work around it outside, trying to still make use of it, even though it doesn't quite do what we want anymore. And then after a bit, we have to throw it away and start again. It's difficult to maintain software over, let's say, a timescale of decades. Now,
that makes sense.
In a statically typed language, my impression is that it's much, much easier to confidently refactor and maintain and develop and enhance software over a decade-like timescale. Oh, here I have one data point, which is GHC itself. It's 150 or 200,000 lines of Haskell, and we're still doing major heart-lung, transplants in Haskell, in GHC, with a degree of confidence, because when you modify your code, of course, that doesn't guarantee that you got it right, but the type system's incredibly good at telling you all the places you need to modify. So long-term maintainability, or sort of total cost of ownership kind of argument, I think is a absolute killer for static type systems, but surprisingly little discussed. I don't know why.
Now that you mention it, I can think of many very long-lived projects written in statically typed programming languages. I'm not sure that I can think of as many that are written in untyped programming languages. It would be interesting to collect some data about that.
Yeah, it would. It really would. So then if you're going to have a statically typed language, because you care about longevity, then you want the type system to be as rich and expressive as possible so that it can express more of what you want. So I see Haskell as a laboratory in which we're really pushing the idea of static typing and saying, how far can you go? Like, start, as it were, from static typing as the world's most successful formal method, right? One that is widely deployed and used by working programmers, and push the bar higher and higher, right? So we've got monomorphically typed language and we get polymorphic type languages, and Haskell sort of tries to push the thing as high as you can go and still maintain this. We just do it every time we compile, so that type inference has to be predictable and fairly fast. But you want the type system to be as expressive as possible. So it's a laboratory in which we explore that idea.
That's very cool. And it's clearly it paid dividends. So, the types are a very important thing to Haskell, but we've rarely even talked about laziness. All we've talked about laziness is we've mentioned that functions decide when their parameters are computed.
Yeah.
It's not, their parameters are not computed before the function is called necessarily. And this sort of relates to the Haskell concept of purity as well.
Yeah.
And I was thinking maybe you could discuss that a little bit.
I've given quite a few talks about this over the time. Particularly, there's a talk called Escape from the Ivory Tower, I think, or my keynote pop a long time ago, that describes this. But laziness was the war cry that brought that particular group together. At the time, lazy functional programming was regarded as quite academic, quite exotic, quite, quirky. It was a very inspiring manifesto to cluster around. But what it did for us, in fact, is that in a lazy language, you really can't have side effects. So if I have a list and I pass the list to a function, imagine the function could evaluate the elements front to back or back to front, or just 3 of them or none of them at all. Now, if each of those elements is a suspension or thunk that does some side effects, then you wouldn't know whether things that were printed, in forward order or reverse order, or not at all, or just 3 of them. So side effects in a lazy language, unrestricted side effects, where any function can have a little side effect on the side, so it has type int to int, but by the way, it does some I/O. That is insupportable in a lazy language. Now, in a language like ML, which was strict, it was not insupportable. It was sort of a bit of a hack, but perfectly doable, because the order of evaluation is completely defined. Right? But not so in Haskell. So that laziness forced us to be pure. It kept us true to the idea of purity. It was a bit like wearing a hair shirt, like in a sort of slightly ascetic way, right? We will stick to the idea of purity. And I now regard sticking to purity as a much more important tenet of Haskell than laziness. Just saying Haskell is a laboratory in which to explore the idea of really sophisticated type systems without subtyping. How far can you push parametric polymorphism? Haskell has also been a laboratory in which to explore the idea of purity, remorseless purity, with no compromises, because compromises are just, they just mean you can't reason about your program at all. For about a decade, that meant our language really didn't have any I/O, or had very clumsy I/O. So it was pretty academic. But then Phil, again, and I work with him closely on this, had the idea of using monads to constrain effects. So that led first to his paper, Comprehending Monads, and then we wrote a paper called Imperative Functional Programming, which said the way to do I/O in Haskell is through monads. So monads provided us a way to combine the purity of Haskell with side effects, with the two not being sort of smushed up together in a bundle that meant you couldn't reason about your program anymore, but with the type system keeping them sort of hermetically sealed from each other. And that proved to be very, very influential, as it turned out. So the whole Monads thing, which is, again, spread into many other languages, was ultimately driven by our embarrassment over our lack of I/O and effects. And again, appropriating an idea from Phil's original paper, Comprehending Monads, was drawn directly from work by Eugenia Moggi, who is very much a theoretical computer scientist and who wrote papers that I, barely understood about what a monad is and how you might use it. And Phil described how to connect that with the world of programming. And that enabled us to reconcile purity and laziness with I/O and side effects. And that was an amazing step forward.
And there's this thing that almost feels like it happens again and again with Haskell, where someone will come up with an idea that maybe seems motivated by some very obvious motivation, and they'll implement it, like typeclasses or monads, for example.
Yeah.
And then as soon as it's implemented in the language and it's available and people start using it, they start having all kinds of ideas for other ways that they can use it. They push it much farther than I assume it was ever envisioned that it would go.
That's right. Yeah, so monads have proved far more influential and important than we thought. And they have given rise to their own sort of zoo of things like, applicatives, which are sort of like weaker than monads, but still stronger than zero. Oh, it's just another zoo of type classes that have grown up around the monad thing. Yes. So again, much more pervasive than we originally expected.
And people, build on, there's monad transformers, which try and work around some, the idea of composing monads together.
Yeah.
And
another interesting thing happened with transactional memory. Do you know what transactional memory is?
I've never actually used it. So my understanding is that instead of using a lock, when you have two cores maybe accessing the same data at the same time, instead of having to prevent the cores from stepping on each other's toes by locking, you instead have any core that's reading, it just does all the reads it needs to do. And then once it's done them, then it checks a log to see if anyone wrote to the memory while it was doing those reads.
Yeah, you're describing the implementation, but the programmer's interface is this. You say, begin atomic transaction, and then do lots of side effects on mutable state, like, insert something into this queue and remove it from that, add something to somebody's bank account, remove it from another. And then you say end transaction, right? And those mutable side effects, like no other thread can see the fact that you've removed something from one bank account without also seeing that you've added it to the other one. So a transaction is seen either not at all or in its full glory to other threads, right? And it's called transactional memory because this applies to the mutable state in memory. Transactional memory makes it much, much, much easier to write correct concurrent programs. Just vastly easier. It's incredibly good abstraction. Much easier to use than locks.
There are lots of people who have only ever used locks, and so they might say, what are you talking about? Locks are fine.
Oh.
But the main problem that locks don't solve is if I have one resource behind a lock and another resource behind the lock, another resource behind a different lock,
Yeah.
and I want to do something with both of them, then it almost feels like I need a third lock that controls whether both of them are locked.
Well, the natural thing to do is say, I'm moving money from bank account A to bank account B. So lock A, lock B, then move, then unlock A and unlock B. But what happens if another thread is simultaneously moving stuff from B to A? Then he'll lock B and then lock A. So if you're unlucky, then the first one will lock A, the second one will lock B, and both of them will get stuck. You get deadlock. So deadlock is tricky, and then you have to work around that. And then there's lots of paradigms like hand-over-hand locking, or you want to reduce the lock range as much as possible. So it turns out that for some operations like, manipulating a doubly linked queue, you can get a research paper from the correct locking protocol for manipulating a doubly linked queue. Whereas in transactional memory, you just say begin transaction, mumble, mumble, end transaction, you're done. It's like incredibly much better. So it moves some problems, not all. Some problems are satisfactorily and easily solved with locking, but it moves some problems from the world of it's a research paper to do this to any, a beginning programmer could do it. Now,
and they do it in the natural way they would do everything.
Yeah, just do it in the natural way. Just say, I just want to say all of these effects should be visible at once or not. What could be easier than that? Now, the idea was out there, but when I worked with Tim to say, well, can we use this for Haskell? Then it wasn't long before, we'd invented a special monad, the STM monad for dealing with this, and transactional variables with a different data type. And we automatically got for free that you could not touch a transactional variable outside a transaction. It was statically rejected by the type system. And you couldn't manipulate a non-transactional variable inside a transaction. Moreover, we invented retry and or else, which are crucial primitives for making STM compositional, so-called. There's a whole paper about this called Composing Transactions or Composable Transactions that I wrote with Tim. So we made STM much better by putting it in Haskell. And then, interestingly, there was a period of about 10 years in which transactional memory was all of a swither in mainstream world. And then everybody drew back. Why did they draw back? Microsoft abandoned, for example, after really a big investment, Microsoft abandoned transactional memory for .NET. Why? Because it was too hard and too non-performant to get right. But in Haskell, transactional memory was dead easy to get right and very performant because Haskell limited side effects. The trouble with in .NET is that everything is a side effect. Computation happens through side effects. So in principle, every single memory interaction needs to be tracked by the implementation. Not so in Haskell. Only the explicit read tvar and write tvar. So it turned out that, very ironically, the place where transactional memory, which is about imperative functional programming, it's a very imperative construct. The place where STM is flourishing is in GHC. STM comes in the box with GHC along with concurrent programming, and it's been working, for the last 20 years or so. And we get very few bug reports about it. Lots of people use it for building concurrent programs. So STM, an imperative construct, is flourishing and usable, in a nobody talks about it, it's so straightforward kind of way, in Haskell, whereas it's been abandoned by the mainstream.
It's beautiful because it's built on abstractions that Haskell already had for other reasons.
Yeah.
And it just happens that they ended up being super useful for this.
Yeah.
It allowed a whole new school of programming that is impossible otherwise.
Yeah, that's right.
Like I said, I feel like this happens over and over with Haskell.
Concurrency works well in many languages, but I think it works very particularly smoothly in Haskell because of STM. And, you can really have a lot of threads. They're often called green threads in other contexts. So they're very, very lightweight.
With no locks. I mean, it's just something that a lot of people would be very surprised by.
Yeah. I mean, of course, Haskell provides something a bit like locks called mvars, which are, again, a little bit better than locks, but basically the same kind of thing. And it's done those for even longer than STM. But STM is a sort of I think it's just the way to write concurrent. By concurrent, I mean parallel I/O performing threads which are each doing input-output and mutating the state in the real world and in the shared memory that they share, but that they may modify the shared memory transactionally.
Let's say that I'm a C# programmer, and I really wish I could use software transactional memory.
Yeah.
Is there anything, maybe not even for software transactional memory specifically, but what can other languages steal from Haskell that you think maybe will catch on in the future, but hasn't yet caught on in such a big way?
Oh, I don't know. That's hard to know. I hesitate to pontificate about what other languages might do. But you can point to many, many instances in which other languages have adopted in some form an idea that was first born in Haskell. STM is not such a thing, incidentally. STM was born outside Haskell, but has flourished inside and been abandoned outside. But, comprehensions and, link in C# was consciously modeled on Haskell. There's many examples of idea transfer, and maybe that's Haskell's real role. It's not that it should ever be a mainstream language adopted by everybody, but that it should continue its role as a seedbed and laboratory in which to develop ideas. I mean, I'd love to see it yet more widely used, but actually I think that imitation is the sincerest form of flattery. I hesitate to suggest any things that have not been adopted yet that might be in the future.
Well, fair enough.
Yeah.
It's always, fraught to predict the future. I mean, you never know, maybe someone will come up with something even better tomorrow. So.
And also I think Haskell has moved into a phase in which it kind of feels like it's more consolidating. Linear Haskell was indeed a huge new increment that's essentially still an experimental feature. But mostly the innovation curve has leveled out. We're into make everything fit together and just work beautifully and improve error messages and make it more stable over time and make enhancements that just eliminate friction. Yes, we're not making radical new extensions so much all the time.
In the Haskell ecosystem overall, including everything from the compiler to the libraries to the text editor, is there anything that you would like to see changed? Anything where if someone wanted to help out, they could jump in?
Oh, yes. So initially, Haskell was closely identified with its compilers. There was more than one at one stage, but essentially GHC has become the brand leader. Compilers are such big investments, it's really difficult for a community to maintain more than one. So GHC is the Haskell compiler, but it's now, again, 25 years ago, we started to think hard about libraries, and that led a group to develop Cabal and to Hackage. So we've now got an ecosystem of libraries and tools that sit around that are crucial to making Haskell work at scale. Absolutely crucial. Nowadays, if you say, please install this, Haskell application, you'll see that Cabal's running off and compiling, like 100 libraries that you indirectly depend on. It's just amazing. It just worked. And Stack is another example. Hackage is the place where all the libraries live. So Haskell ecosystem has moved decisively towards not just being a compiler, but being a whole collection of surrounding tooling and libraries. Oh, and then the HLS, the language server, Haskell language server that lets you build an IDE. So the fragility of that ecosystem is entirely an open source ecosystem run by volunteers, each of whom have their own constraints and priorities, and they're all busy and they're all working hard. And it's easy for that to become uncoordinated, so GHC accidentally does something that screws up life for Cabal or vice versa. It's all these pieces have to work flawlessly together for the end user experience to be seamless. Some years ago, we recognized just having these free-floating volunteer groups was not serving our end users very well. So together, a bunch of us developed and launched the idea of the Haskell Foundation. So it's meant to be a non-profit organization whose goal is not to take over these groups at all, but to rather serve as sort of glue to help them do their best work, if you like, and obtain resources and help fill in the gaps for the boring but useful things that have to be done to make the experience seamless. But which teams of volunteers don't find nearly as motivating because they're just boring and useful. The biggest challenge I think we face is that Haskell doesn't have a single corporate sponsor. Many programming languages have a company that supports its ecosystem. So Swift has Apple and Go has Google and so forth. Haskell doesn't really have any company that is, we're the company that supports Haskell. Or even OCaml now has Jane Street, right? Is effectively OCaml's corporate sponsor now. Now, the trouble with open source projects at scale, and Haskell is clearly at scale, that lack a single corporate sponsor, is the tragedy of the commons, right? Everybody wants to use it and nobody wants to pay for it. So the Haskell Foundation is trying to at least ameliorate the tragedy of the commons by providing at least a credible vehicle to which you can donate, right? Time or money. Whereas previously, if there was no credible vehicle, how would you help, right?
Yeah, if you wanted a sponsor, who would you even know to give the money to?
Exactly. But now the question is, how can we make the case in a way that makes sense to businesses? Because, I think the businesses are getting value from Haskell. I want to say, well, look, you pay for your use of Amazon Web Services or Azure. You pay for your phone. You pay for your internet access. All of these are things on which you rely in a mission-critical way, and you don't even think about paying for them. Of course, you pay for them. It's just a business line, just a business expense. Haskell and GHC you happen to be able to get them for free. But that doesn't mean that they come for free. It means that somebody else is paying for them at the moment. But I would love people who use Haskell in a mission-critical way to position contributing to the Haskell Foundation in the same way that they position any other business expense. It's a cost of doing business. Because they're relying on that ecosystem for the very things that are giving value. They're getting actual value from it, in effect. Their business relies on it. And if collectively we don't do that, then we'll eventually, volunteers will burn out and, the ecosystem will become ragged at the edges. So that's our principal challenge, I think, is sort of getting past this tragedy of the commons thing to the point where, every company should think, of course we belong to the Haskell Foundation. How could we not? It would be bad for our business if we didn't. And I'm looking for help for people to say, how could we make it a no-brainer? I'm not a business person. I don't run a company. I would love help with this. But it's very important. The Haskell Foundation should not rely on the generosity of 2 or 3 donors. It should have a donor base of tens or hundreds of companies, lacking any one, but we don't.
Yeah, and this is a kind of a pervasive problem as well. I mean, anyone who's worked for a company, if you see a library that says you may want to use it and it may be helpful for your company, but even if it says, you must spend $100, you must give me $100 to use this library, most people are not going to, go through the trouble of talking to their boss and saying, hey, we need to figure out how to pay this guy.
Yeah.
typically it's just something that's not really done
Yeah.
outside of a few exceptions where you're getting a really big thing like a
But it
game
shouldn't
engine.
be trivial. It should be, oh, I'm spending $1 million a year on the salaries of Haskell programmers. So of course I should, spend 1% of that on making sure that the ecosystem on which those programmers rely every day remains healthy. So then it's not $100, it's like $100,000. No, or 10,000. Well, what was it? What's 1% of your $1 million? $10,000, right? So it becomes a significant sum, but then you're spending a lot on the salaries of the people who are relying on this ecosystem. I don't know how to square. So I suppose I'm cheekily using this podcast as a way to invite listeners to say, "Oh, I could figure out how to help with that."
I'm sure there's going to be many people listening who want to help. So
So there's way to help. Will be one way to solve the process problem. How can we make it the Haskell Foundation is busily thinking about how could we frame offers in a way that companies could easily make it a line in their project proposal. But another is there might be people who just want to contribute time or money directly. We ought to make that easy. So anything would be helpful. It's just how do we solve the tragedy of the commons?
So I scheduled an hour of your time, and it's already been like an hour and 20 minutes. So I don't want to go too much longer, but I wanted to ask one last question. What keeps you excited about programming language research after all these years?
So I think for me, it's always been about trying to take simple, elegant, and beautiful ideas and turn them into a practical reality. I'm so happy that Haskell remains pure, right? That we didn't sort of somehow find a hacky compromise. Not that these ideas are necessarily better than anybody else's, but I like the idea of taking a few simple ideas and just pushing them really hard. And I feel privileged to have been, throughout my professional life, people have been willing to pay me to do things that at time might seem fairly impractical, but to, take one idea or a couple of ideas and really run with them. So I have found very motivating and inspiring the fact that some of these ideas are found inspirational and useful by people who are just doing a day job, right? Not just by pointy-headed PhD students in computer science universities, computer science departments. I love the fact that people out there in industry are using type classes and type families and some pretty complicated types, actually. Some of our bug reports come from people who are doing, I look at their code and I think, wow, that's really scary. They're doing pretty exotic things, right? Because they care about longevity. So I find it very motivating, taking fundamentally simple ideas, trying to incorporate them in a practical tool that people can actually use, and then getting feedback from people using that tool. That's quite motivating. So in the end, it's justified by impact, I suppose. I often say that computer science research is a bit like a fractal, right? You can always invent a new programming language. You could do one every day of the week, but it wouldn't matter, right? Nobody would care. Unlike physics, say, when if you're discovering something new about the physical world, that's a result. But inventing a new programming language, not a result, right? So novelty in computer science is of no value in and of itself. You must have utility. That's the proof of the pudding. What excites me about Haskell is the combination of elegance and beauty and actual utility.
I think that's really interesting because I think you see it in many other places where people sort of pursue something simple and they just pursue it as far as they can go, and sometimes it goes very far. I can't remember who, but there was some famous mathematician or physicist who said that he only had like a few tricks and he just applied them every time he saw a new problem, and sometimes they worked really well.
Yeah.
Kind of similar to how you apply Monads for STM and it works great. It might not work great for everything, but
Yeah, that's right. So it's not that Haskell is better than anything else. It's just that it's So in some ways, my whole professional career has been like a one-trick pony, or maybe two. Right? But there's merit in a few people pursuing a trick a long way, just to see where it goes, and then maybe when you see where it goes, perhaps you can take ideas from them, use it to infect things more broadly.
that's brilliant. Thank you so much for your time. It's been a pleasure talking to you.
That's been great talking to you too. Yeah.
I hope you enjoyed listening to that podcast. I know I enjoyed making it. Simon Peyton Jones is so smart, but so humble. Not every day you get to meet someone like that. Anyway, you probably noticed that I'm a pretty small channel, and it would really mean a lot to me if you subscribed. In fact, if you press the subscribe button, most likely I'll immediately get a notification, and that will immediately make me smile. So if you want to be the proximate cause in that chain reaction, hit that button. If you really like the video, you might also want to follow me on Twitter. For example, I have a post on the Android Calculator app that many people seem to enjoy, so check me out there too. One last thing, if you really liked it, you can join my Discord server where we talk about math, programming, all kinds of things. So anyway, thank you very much for watching and have a nice day.